Here's another problem for the afternoon session that's built on the same, there are a couple of problems built on the same figure. They show you this figure right here, and they tell you that this is bounded by the curve y equals x squared, y equals 0, and x equals 4. So it's kind of a triangular area with a scoop out on one side. And they ask you some things about it. One of the things they ask is, what's the area OAB? And the next thing they ask you is, what is the first moment of the area OAB about the x-axis? And it's not a bad idea to read those two problems before you start working. Let's see how it proceeds. I've redrawn it here. Given the area OAB bounded by y equals x squared, y equals 0, and x equals 4, determine the area AOB. Well, we set up a differential area y dx. We set up our differential element this way, and we know that y is equal to x squared. So we can find the area by integrating from 0 to 4 x squared dx. And that gives us x to the third power divided by 3, evaluated between 0 and 4, and we get an area of 64 divided by 3. Now we're asked next to determine the first moment of that area about the x-axis. Now, that requires just a little bit of manipulation here. The differential moment about the x-axis, we take the differential area times the distance up to its centroidal axis. Well, its centroidal axis is up there a distance of 1/2 y. There's the 1/2 y times dA. So dm sub x is 1/2 y squared dx, or 1/2 x to the 4th dx. Down here we find the total moment by integrating over the range from x equals 0 to x equals 4. So we have the integral from 0 to 4, half of that integral, x to the 4th dx. Here's the half that's out in front. The integral of x to the 4 is x to the 5 divided by 5, evaluated between 0 and 4. 2 times 5 is 10, and 4 to the 5th is 1,024. So we end up that the first moment is 512 divided by 5. Now, that finished the sample problems that we were given for that particular set of problems. We're going to take some example problems now from this manual that you have for studying for the Fundamentals of Engineering examination. This is the EIT review manual put together by Lundeberg, and that's a very fine manual. And I'm going to pick problems that come from the beginning, let's see, they're not numbered, but they're at the beginning of the mathematics section. And it's topic Roman numeral 3, mathematics, time limit, 45 minutes. So we're going to see how these problems go. I think you're going to be pleased with the fact that we'll be able to go through them a little bit easier, and perhaps in less time than the time limit quoted there. Now, I have made photocopies of that thing so that I can move them back and forth out of there easier than handling the manual itself. But if you'll follow along with me, beginning with problem number 1, where it says, what is the general form of equation for a line whose x-intercept is 4 and whose y-intercept is -6? If you'll start at that point and follow along with me, we should get along pretty well. Now, this is a Lundeberg diagnostic exam. I don't think that fellow's an Irishman. The general form of the line, if we draw a picture of it, this thing is going to cross the x-axis at x equals 4, y equals 0, and it's going to cross the y-axis at x equals 0, y equals minus 6. You can go through and derive the equation. You can use y equals mx plus b, and you can calculate all of this stuff out. But that's not the way to work this problem quickly. You had a list of equations. Put any one of these points, say 4, 0 in it, and you will find it satisfies two of them. Put the other 2 points, 0 and minus 6 in it, and you will find out it satisfies 2 of those, and only one of them overlaps. So consequently, you do end up with a solution, and it happens to be item C. There's one of them that doesn't work for those points at all. Now, the next one of them gives you a problem, and I hope I'll be able to demonstrate a calculator on here, because it gives you the problem that it says the cosecant is minus 8/5. What is the cosine of 2 theta? Yes, as a genuine, bona fide, tenured professor, I should encourage you to go ahead and do this by trig identities, because that's the real way. However, as my students would point out to you, there is another way to do this. Take your trusty calculator, and you have the cosecant is 8/5. Now, minus 8/5 to be exact. The cosecant is 1 over the sine. The cosecant is 1 over the sine. That means the sine is minus 5/8. Okay? Well, with the calculator, and I'm trying to see whether I can get this so that the glare is not on it. It looks like it's working. I can take this calculator, I can do a 5 enter, and I can do an 8 divide, and I can do a change sign, and I now have minus 0.625 sitting in the calculator. And I can say, Mr. Calculator, what angle would give me a sine of that value? And the calculator says that angle is 38.62 degrees minus. Well, that's nice. Let me take that angle and multiply it by 2. I now have the angle of minus 77.36. And I can say to it, what is the cosine of 2 theta? And it tells me the cosine of 2 theta is 0.21875. Well, that is really wonderful, except for the fact that all the answers to that thing are quoted in terms of quarters, eighths, sixteenths, and 30-seconds. So what I did with this thing is say, well, nuts. Let's take this 32 times and let's see what we get out of it. And it's 7 30-seconds. 7 30-seconds, and that happens to be answer A. Now, that's the way to get through the exam without taking just a whole lot of time. And you are allowed to take to the examination a calculator of your choice. It doesn't necessarily need to be a Cadillac, but I can tell you when Dr. Lowry and I were proctoring this exam a couple of years ago, maybe not quite that long, at any rate, I noticed that the students were using a particular calculator, a bunch of them, and I walked around the room, and 95% of them had a Cadillac type calculator. That is something like the top line TI calculator or the Hewlett-Packard 48GX. The kids really didn't pull out any stops in getting their calculators, and a lot of them really practiced using them, I know. The third problem in this asks you, what is the rectangular form of the polar equation r squared equals 1 minus tangent squared? Well, that may seem like a formidable problem. It really isn't. R squared is equal to 1 minus tangent squared. But r squared is x squared plus y squared. It's equal to 1 minus tangent squared. The tangent is y divided by x. Well, to get it in the form that's listed in the answers available, you multiply through by the x squared and collect the terms on one side, and you immediately find out that it's item D. Okay. The next one, number 4, I should have written out in separate form, but I didn't. This is one of those problems that solves itself very quickly. This is number 4. Slide it around here so you can get a good look at it. For 3 matrices, A, B, and C, which of the following statements is not necessarily true? Now, A, B, and C have to have some properties in common for any of these to be possible. For example, if you're going to have either A plus the quantity B plus C, or the quantity A plus B plus C, they all have to have the same number of rows and columns. But if they do, that works. Furthermore, if A times the quantity B plus C is possible, then AB plus AC is possible. Furthermore, if the addition started the other way around, this is just changing the order of addition, that works. The one that is subject to discussion is this fellow right here. The quantity B plus C times A is not necessarily the same as AB plus AC. And the reason that's true is that the order of multiplication for matrices is not necessarily preserved if the order is reversed. That is, the result is not the same. A times B is not necessarily the same as B times A. Okay? Now, that one is fairly easy. You can get that one by inspection almost. The next one gives you 3 vectors and asks you to calculate A dot B cross C. We set up the determinant I, J, K. The next line is the vector B, 1, 2, 3. 1, 2, 3. The third line is the vector C, 3, 4, 5. And we use the determinants and calculate them out, and we come up with this vector minus 2I plus 4J minus 2K. The dot product A times that vector is going to give us 6 times minus 2 is minus 12. 8 times 4 is 32. And 10 times 2 is minus 20. So 10 times a minus 2. So I get minus 12 and minus 20 gives me minus 32 plus 32 gives me 0. Here's one dear to the hearts. I think they put this one in specifically for people in your business. Here we have a probability problem. A marksman can hit a bullseye from 100 meters with 3 out of every 4 shots. Now, I assume you fellows are each a better shot than that, so we're not going to argue with you. But what we have here is that the probability of a hit on a given shot is 75%, 3 out of 4. What the problem asks you is, what is the likelihood that this marksman will score at least 1 bullseye with the next 3 shots? Let me repeat that. What's the probability that this marksman, who has a likelihood of hitting 3 chances out of 4 every shot, is going to hit at least once in the next 3 shots? Well, you know that's going to be a real high probability, right? His probability of hitting each time is 3/4, so his probability of missing is only 1/4. And it's actually the missing part that's the easiest way to work this problem, because the likelihood that he's going to miss 3 times in a row is just the cube of the probability that he'll miss on once. So that's 1 chance in 64. The chance that he's going to hit more, 1 chance or more is 1 minus that, or 63 over 64. You don't want to mess with that guy if he's got 3 bullets left in his gun. Not unless you're really brave or tired of living. The next one, in fact, I think I worked them out of order. That was number 7, and this is number 6. This is Aggie land. Occasionally we do get confused. The problem number 6 is a geometric progression. It tells you that the second term in a progression is 3 over 10, and that the sixth term in the progression is 243 divided by 160. And it asks you, what's the first term? Well, we know the second term is the first term times the r, the rate. We also know that the sixth term is r times the fifth, r squared times the fourth, r cubed times the third, and r to the fourth times the second one. Well, that's handy, because that lets me say that 243 is equal to 3 over 10 times r to the fourth. I solve for r to the fourth, and I find out that it's 81 divided by 16. That's a very handy number, because I can take the fourth root of both 81 and the fourth root of 16 and find out that r itself is just 3 halves. So T2 is 3 halves. It's equal to T1, or excuse me, T2 is 3 tenths. It's T1 times 3 halves. So T1 turns out to be 1/5. Okay, that was... Okay. The next one requires a little discussion, because we're going to need to do some pulling things out here. The final scores of students in a graduate course are normally distributed with a mean of 73 and a standard deviation of 11. What is the probability that a student's score will be between 65 and 80? And it gives you 4 values. They're not all that widely spread. You go from a low of 0.42 approximately to a high of about 0.65. So guessing in this is probably not going to be too spiffy. There is a table in the manual for which I am reaching. There is a table, and there is also a found it relatively easily. We have the table of normal distribution. It's on page 9 of your manual. And preceding that, in the business on probability, you have a section that deals with normal distribution. And if we could zoom a little bit on that equation right there for f of x, you will notice it has an e to the minus parenthesis x minus mu quantity squared divided by 2 sigma squared. Sigma is the standard deviation, mu is the mean, and x are the scores. You don't need to worry about the rest of this stuff over here, because we're going to pick it off of this table in just a minute. Now, I lost the problem. There we go. We have a mean of 73, a standard deviation of 11, and we're supposed to figure out the probability that a student's score is going to range between 65 and 80. Now, we figure this x value, as I called it here, s minus mu divided by sigma. Remember, that was in that exponent. And we get a value for the lower one. The mu is 73, the score is 65, and I wrote these down in the wrong order. That's why it's minus 73 plus 65. And it comes out to be minus 8 over 11, which is approximately 0.73. It's actually minus 0.73. And we're just going to use minus 0.7. Round it down. Similarly, x2 is the score, 80 minus 73, the average, divided by 11, and we get plus 7/11, which is approximately 0.6. We need the area under the normal distribution curve between minus 0.7 and plus 0.6. Here's the way you do that. Notice that this table has a bunch of pieces in it. One of them has the area from minus infinity all the way up to x. Another part of the table has the area from x on up. Furthermore, you notice that this table is symmetric. Right? Notice these curves are all symmetric. So the fact that it only gives you the area from here on up, it also could have given you the area from minus infinity up to x. Okay? And that's what gets us across the creek right here. We pick, I'm going to be switching back and forth here for a minute, so it may get a little hard to follow, the probability that it's going to land between 65 and 80. You take the probability for everything from minus infinity up to plus 6. And I'll show you in the table where this figure of 0.7257 comes from this 0.6, f of 0.6. Then you subtract off the r of 0.7, 0.2420. Let me show you where those values are. Here is 0.6, and I'm coming across the table, and right there is the 0.7257. That's the first value. On just the line below, I go across one more, and I'm subtracting off minus r of x. Remember that that area is the same as the one coming up to here, and that's the 2420. So when I subtract those two things, I come up with the value exactly as quoted in the answer, the 0.4837, and that happens to be answer B. So it wasn't nearly as bad to work. Most of the normal distribution problems you'll encounter that I have ever seen in these exams are relatively straightforward. They're not too bad. The next one asks you to evaluate a limit. A limit as x approaches 0 of 1 minus e to the 3x divided by 4x. If you blindly proceed to put x equals 0 in this thing, the numerator becomes 1 minus e to the 0, and e to the 0 is 1. So you get a 0 in the numerator. Well, that's not so bad. But when you put x equals 0, you also get a 0 in the denominator. So you've got the ratio 0 over 0, and there's no way to tell, at least initially, what that ratio ought to be. L'Hopital's rule, which is in the manual, we mentioned it earlier, says take the derivative of the numerator, which in this case is minus 3 e to the 3x. Take the derivative of the denominator is 4x, its derivative is just 4, and once again take the limit, in this case, as x approaches 0. And we're going to get a limit of minus 3/4. Okay? So that's the way it worked. This is an interesting question, the next one, to give to a bunch of folks who are going to take the fundamentals of engineering examination in the great state of Texas, at least down here as far south as we are in College Station. Because the next one, I got to read this statement to you. I realize that you guys are a little farther north and you're more in the continental climate than we are down here in the oven of Houston, or at least the Houston weather. It says the radius of a snowball rolling down a hill is increasing at the rate of 20 centimeters per minute. That is not a likely event in College Station on two scores. One, a snowball would have a heck of a time rolling anywhere for a whole minute in College Station. And secondly, it'd have a pretty difficult time finding a hill in College Station. How fast is its volume increasing when its diameter is a meter? All right. Now, it's a well-stated problem, and these kinds of accretion things do occur. If they wanted to make this a Texas problem, they should have used hailstones, because the differential equation governs them. In this case, we have a snowball. We're told that the rate of increase of its radius is 20 centimeters per minute. And they ask you, what's the rate of change of its volume when its diameter is a meter? Well, we do have to remember that if its diameter is a meter, its radius is a half a meter. And from those formulas on mensuration that you're given, you can readily find that the volume of a sphere is 4/3 pi r cubed. You can differentiate that with respect to time and find out that the time rate of change of the volume is 4 pi r squared dr by dt. From here on, it's just a matter of substituting in the numbers. dv dt is 4 pi, the radius is 1/2 squared, and the rate the radius is increasing is 20 centimeters per minute, which is 20 over 100 meters per minute. And we end up with 0.2 pi for the result, and that's 0.63 cubic meters per minute is the rate of change of the volume of this snowball. There were a lot more of those snowballs where I did my graduate work at Cornell University in upstate New York, especially this time of year. Now, here we are evaluating another integral. And this again is a continuation of problems out of your study manual from Lüneburg. We're asked to evaluate the integral cosine squared x times the sine of x dx. You will not find that listed directly in your table of integrals, but you will find in that table of integrals a number of things that shows you how to integrate by parts, by trig substitution, by completing the square, and other methods. In this particular case, I do a substitution. Let u equal the cosine of x, then du, differentiating this, is minus sine x dx. So I look at my original integral, I put a minus sign in front of it, write the cosine squared, and put the sine of x dx in parentheses along with a minus sign, and I've got an integral of the form minus the integral of u squared du. Well, even Aggie profs in mechanical engineering can integrate that one. And it's minus 1/3 u to the third power plus a constant. And we end up with the integral then, substituting back here, minus cosine cubed of x over 3 plus an arbitrary constant. The next one you have to read like a Philadelphia lawyer, because it asks you to find the area bounded between a curve and an axis, as well as two limits. I'm going to lay it on top here for just a minute. What is the area of the region bounded by the curve y equals sine x and the x-axis on the interval between x is equal to pi by 2 and x is equal to 2 pi? Well, I plotted this out. And you'll notice that for 1/3 of this region, namely from pi by 2 to pi, the area is above the x-axis and would therefore be positive. But for 2/3 of this region, it's below the axis and would be negative. If I were to take the standard integral from pi by 2 to 2 pi of the sine of x dx, I would get left over just this little part in here, because this area would cancel the one over here. So I have to do a sign change. I integrate from pi by 2 to pi, that's that part, and then I take the negative of the integral from pi to 2 pi. That'll give me a positive result for the area. The integral of the sine of x dx is minus the cosine. The limits, the first part, are pi by 2 to pi, and in the second part, they're pi to 2 pi. Remember the change of sign here. And when I add it all up, I get 3, and that's one of the answers listed. I have to admit, that's not one of my favorite problems in here, because it's one of those kinds of problems that's likely to start arguments. about what did you really mean when you wrote that down. And that's one of the things that makes teaching challenging. Try to explain to irate students why they shouldn't have misread that problem statement that was eminently clear to you. Here's another problem. What is the general solution of the following differential equation? Y double prime minus 8y prime plus 16y is equal to 0. Using the technique of the book, y is equal to a constant times e to the rx. The auxiliary equation is r squared minus 8r plus 16. That factors into r minus 4 times r minus 4, and it gives me repeated roots. So the solution is c1 e to the 4x plus c2x e to the 4x, and that corresponds to solution B. Excuse me. The next one, number 14, is a Laplace transform problem. And number 14 states, find the Laplace transform of the equation with the given boundary conditions. Let me slide that up a little bit. The boundary conditions are f prime of 0 equals 0 and f of 0 equals 0. While he calls them boundary conditions, a number of you, particularly electrical engineers, would consider those as initial conditions. The differential equation is the second derivative of f with respect to t plus f of t is the sine of beta t. There's an interesting point between Lüneburg and the manual at this stage. The manual points out that the Laplace transform of the second derivative is indeed s squared f of s minus s times 0 minus 0. The Laplace transform of f of t there is f of s. But interestingly, the manual does not have the Laplace transform of the sine of beta t. It is beta over s squared plus beta squared. And when you solve this equation, you get f of s is equal to 1 over 1 plus s squared times beta over s squared plus beta squared. Obviously, all of us who work with this fundamentals of engineering exam really hope that we don't have any inconsistencies between the actual exam and the manual. Inconsistencies in the sense of asking for things that you would normally have to look up in a table, but the value, for some reason, is not in the manual. Now, the last particular problem in this one is a Newton's method. It's the only Newton's method I have ever seen in a sample problem. And I'm not sure whether this one was taken from an actual exam or not. I suppose it was. It gives you a function of x, which is x minus 2 quantity squared minus 1, and it asks you to use Newton's method to extract roots. But in particular, it wants to know what is the third iteration if you started with x1 equal 9.33. Believe me, that's an odd place to start. Usually when we make a first guess, it's a whole number. Why in the world would you pick 9.33? But we will not question. We will proceed. Now, in Newton's method, the n plus first guess is equal to the previous guess minus the function evaluated at the value of the previous guess divided by its first derivative, evaluated at the same place. We can look at the original function, x minus 2 quantity squared minus 1, and we can readily calculate its first derivative, which is just going to be 2 times x minus 2. Now, f of x1 is 9.33 minus 2, quantity squared, minus 1, and that comes out to be 52.73. There's actually some extra stuff hanging on the end of that, but you don't need to worry about it. Its first derivative at that same point comes out to be 14.66. Using the equation for Newton's method, we get that x2 is equal to 9.33, which is the previous guess. The value of the function, 52.73 divided by 14.66, its slope. That division gives you 3.60. Subtracting it from 9.33 gives you 5.73. We go through that process once again. F of x2, 5.73 minus 2, quantity squared, minus 1 gives you 12.92. F prime comes out to be 7.46. X3 comes out to be 5.73 minus 12.92 divided by 7.46, which is 4.0, and that's one of the listed answers. That runs through the first set of problems in Lüneburg. It has given you a set of problems from a previous examination plus an in-depth study of the manual itself. I believe this provides you a good basis for a sound study of the mathematics likely to be found in the fundamentals of engineering examination. Recognize that it starts with things from the very beginning: the equation of a line, the conic sections, the probability and statistics, the things that were related to simple calculus, derivatives and integrals, vector analysis from the standpoint of vector algebra. Notice, for those of you that have had calculus courses in vectors, that there are no problems in divergence, curl, or gradient that are included in this. There are no partial differential equations, although there are partial derivatives. The mathematics content of the exam is reasonable. It is reflective of what is normally practiced in engineering. Most of what we have determined from the way students work with this exam reveal that they find the mathematics part of the exam the easiest. And studies of how people do on the exam show that they score more of their points out of mathematics, percentage-wise, than almost any other. That is encouraging. But it also points out that the mathematics aspect of it is something which you must do well if you're going to be competitive with others taking the exam. I hope you found this useful, and I will look forward to having a question and answer session with you.